A mechanical calculator, or calculating machine, was a mechanical device used to perform automatically the basic operations of arithmetic. Most mechanical calculators were comparable in size to small desktop computers and have been rendered obsolete by the advent of the electronic calculator. Surviving notes from Wilhelm Schickard in 1623 report that he designed and had built the earliest of the modern attempts at mechanizing calculation. His machine was designed for multiplication and division and had an innovative mechanical adding machine built into the base. The surviving notes do not make it clear whether Schickard's machine would have worked as well as he reported to Kepler and might well have jammed when a number of counters were forced to move simultaneously. 2 decades later in 1642 Blaise Pascal decisively solved this particular problem with his independent invention of a mechanical calculator. The comparative roles and significance of Pascal and Schickard's important inventions is discussed in much greater detail in Schickard versus Pascal, an empty debate. Co-opted into his father's labor as tax collector in Rouen, Pascal designed the calculator to help in the large amount of tedious arithmetic required. It was called Pascal's calculator or Pascalin. Thomas' arithmometer, the first commercially successful machine, was manufactured 200 years later in 1851. It was the first mechanical calculator strong enough and reliable enough to be used daily in an office environment. For 40 years the arithmometer was the only type of mechanical calculator available for sale. The comptometer, introduced in 1887, was the first machine to use a keyboard which consisted of columns of 9 keys for each digit. The Dalton adding machine, manufactured from 1902, was the first to have a 10-key keyboard. Electric motors were used on some mechanical calculators from 1901. In 1961, a comptometer-type machine, the Anita Mk7 from Sumla Comptometer Limited, became the first desktop mechanical calculator to receive an all-electronic calculator engine, creating the link in between these two industries and marking the beginning of its decline. The production of mechanical calculators came to a stop in the middle of the 1970s, closing an industry that had lasted for 120 years. Charles Babbage designed 2 new kinds of mechanical calculators, which were so big that they required the power of a steam engine to operate, and that were too sophisticated to be built in his lifetime. The first one was an automatic mechanical calculator, his difference engine, which could automatically compute and print mathematical tables. In 1855, Georg Schiedts became the first of a handful of designers to succeed at building a smaller and simpler model of his difference engine. The second one was a programmable mechanical calculator, his analytical engine, which Babbage started to design in 1834. In less than 2 years he had sketched out many of the salient features of the modern computer. A crucial step was the adoption of a punched card system derived from the Jacquard loom, making it infinitely programmable. In 1937, Howard Aiken convinced IBM to design and build the ASCC Mark I, the first machine of its kind, based on the architecture of the analytical engine. When the machine was finished, some hailed it as Babbage's dream come true. Ancient history. The desire to economize time and mental effort in arithmetical computations, and to eliminate human liability to error, is probably as old as the science of arithmetic itself. This desire has led to the design and construction of a variety of aids to calculation, beginning with groups of small objects, such as pebbles, first used loosely, later as counters on ruled boards, and later still as beads mounted on wires fixed in a frame, as in the abacus. This instrument was probably invented by the Semitic races and later adopted in India, whence it spread westward throughout Europe and eastward to China and Japan. After the development of the abacus, no further advances were made until John Napier devised his numbering rods, or Napier's bones, in 1617. Various forms of the bones appeared, some approaching the beginning of mechanical computation, but it was not until 1642 that Blaise Pascal gave us the first mechanical calculating machine in the sense that the term is used today. A short list of other precursors to the mechanical calculator must include a group of mechanical analog computers which, once set, are only modified by the continuous and repeated action of their actuators. Before Common Era, there are odometers and the Antikythera mechanism, an out-of-place, unique, geared astronomical clock, followed more than a millennium later by early mechanical clocks, geared astrolabes, and followed in the 15th century by pedometers. These machines were all made of toothed gears linked by some sort of carry mechanisms. These machines always produce identical results for identical initial settings, unlike a mechanical calculator where all the wheels are independent but are also linked together by the rules of arithmetic. The 17th century. Overview. The 17th century marked the beginning of the history of mechanical calculators, as it saw the invention of its first machines, including Pascal's calculator, in 1642. Blaise Pascal had invented a machine which he presented as being able to perform computations that were previously thought to be only humanly possible, but he wasn't successful in creating an industry. In a sense, Pascal's invention was premature, in that the mechanical arts in his time were not sufficiently advanced to enable his machine to be made at an economic price, with the accuracy and strength needed for reasonably long use. This difficulty was not overcome until well on into the 19th century, by which time also a renewed stimulus to invention was given by the need for many kinds of calculation more intricate than those considered by Pascal. The 17th century also saw the invention of some very powerful tools to aid arithmetic calculations like Napier's bones, logarithmic tables, and the slide rule which, for their ease of use by scientists in multiplying and dividing, ruled over and impeded the use and development of mechanical calculators until the production release of the arithmometer in the mid-19th century. Invention of the mechanical calculator. Blaise Pascal invented a mechanical calculator with a sophisticated carry mechanism in 1642. After 3 years of effort and 50 prototypes, he introduced his calculator to the public. He built 20 of these machines in the following 10 years. This machine could add and subtract two numbers directly and multiply and divide by repetition. Since, unlike Schickard's machine, the Pascaline dials could only rotate in one direction, zeroing it after each calculation required the operator to dial in all nines and then propagate a carry right through the machine. This suggests that the carry mechanism would have proved itself in practice many times over. This is a testament to the quality of the Pascaline because none of the 17th and 18th century criticisms of the machine mentioned a problem with the carry mechanism, and yet it was fully tested on all the machines, by their resets, all the time. Pascal's invention of the calculating machine, just 300 years ago, was made while he was a youth of 19. He was spurred to it by seeing the burden of arithmetical labor involved in his father's official work as supervisor of taxes at Rouen. He conceived the idea of doing the work mechanically, and developed a design appropriate for this purpose. Showing here in the same combination of pure science and mechanical genius that characterized his whole life. But it was one thing to conceive and design the machine, and another to get it made and put into use. Here were needed those practical gifts that he displayed later in his inventions. In 1672, Gottfried Leibniz started working on adding direct multiplication to what he understood was the working of Pascal's calculator. However, it is doubtful that he had ever fully seen the mechanism, and the method could not have worked because of the lack of reversible rotation in the mechanism. Accordingly, he eventually designed an entirely new machine called the stepped reckoner. It used his Leibniz wheels, was the first two-motion calculator, the first to use cursors and the first to have a movable carriage. Leibniz built two stepped reckoners, one in 1694 and one in 1706. Only the machine built in 1694 is known to exist. It was rediscovered at the end of the 19th century, having been forgotten in an attic in the University of Gar-Paragraph-Tingen. In 1893, the German calculating machine inventor Arthur Burckhardt was asked to put Leibniz's machine in operating condition if possible. His report was favorable except for the sequence and the carry. Leibniz had invented his namesake wheel and the principle of a two-motion calculator, but after 40 years of development he wasn't able to produce a machine that was fully operational. This makes Pascal's calculator the only working mechanical calculator in the 17th century. Leibniz was also the first person to describe a pinwheel calculator. He once said, "It is unworthy of excellent men to lose hours like slaves in the labor of calculation which could safely be relegated to anyone else if machines were used." equals other calculating machines equals, Schickard, Pascal and Leibniz were inevitably inspired by the role of clockwork, which was highly celebrated in the 17th century. However, simple-minded application of interlinked gears was insufficient for any of their purposes. Schickard introduced the use of a single-toothed mutilated gear to enable the carry to take place. Pascal improved on that with his famous weighted sautoir. Leibniz went even further in relation to the ability to utilize a movable carriage to perform multiplication more efficiently, albeit at the expense of a fully working carry mechanism. I devised a third which works by springs and which has a very simple design. This is the one, as I have already stated, that I used many times, hidden in the plain sight of an infinity of persons and which is still in operating order. Nevertheless, while always improving on it, I found reasons to change its design. When, several years ago, I saw for the first time an instrument which, when carried, automatically records the numbers of steps by a pedestrian, it occurred to me at once that the entire arithmetic could be subjected to a similar kind of machinery so that not only counting but also addition and subtraction, multiplication and division could be accomplished by a suitably arranged machine easily, promptly, and with sure results. The principle of the clock for a direct entry calculating machine couldn't be implemented to create a fully effective calculating machine without additional innovation with the technological capabilities of the 17th century. Because their gears would jam when a carry had to be moved several places along the accumulator. The only 17th century calculating clocks that have survived to this day do not have a machine-wide carry mechanism and therefore cannot be called fully effective mechanical calculators. A much more successful calculating clock was built by the Italian Giovanni Pollini in the 18th century and was a two-motion calculating clock. In 1623, Wilhelm Schickard, a German professor of Hebrew and astronomy, designed a calculating clock which he drew on two letters that he wrote to Johannes Kepler. The first machine to be built by a professional was destroyed during its construction and Schickard abandoned his project in 1624. These drawings had appeared in various publications over the centuries, starting in 1718 with a book of Kepler's letters by Michael Hansch, but in 1957 it was presented for the first time as a long-lost mechanical calculator by Dr. Franz Hammer. The building of the first replica in the 1960s showed that Schickard's machine had an unfinished design and therefore wheels and springs were added to make it work. The use of these replicas showed that the single-tooth wheel, when used within a calculating clock, was an inadequate carry mechanism. This did not mean that such a machine could not be used in practice, but the operator, when faced with a mechanism resisting rotation, in the unusual circumstances of a carry being required beyond 3 dials, would need to help the subsequent carry to propagate. Around 1643, a French clockmaker from Rouen, after hearing of Pascal's work, built what he claimed to be a calculating clock of his own design. Pascal fired all his employees and stopped developing his calculator as soon as he heard of the news. It is only after being assured that his invention would be protected by a royal privilege that he restarted his activity. A careful examination of this calculating clock showed that it didn't work properly and Pascal called it an avorton. In 1659, the Italian Tito Livio Burattini built a machine with 9 independent wheels. Each one of these wheels was paired with a smaller carry wheel. At the end of an operation, the user had to either manually add each carry to the next digit or mentally add these numbers to create the final result. In 1666, Samuel Morland invented a machine designed to add sums of money, but it was not a true adding machine since the carry was added to a small carry wheel situated above each digit and not directly to the next digit. It was very similar to Burattini's machine. Morland created also a multiplying machines with interchangeable discs based on Napier's bones. Taken together, these two machines provided a capacity similar to that of the invention of Schickard, although it is doubtful that Morland ever encountered Schickard's calculating clock. In 1673, the French clockmaker René Copyright Grillet described in Curiosities Mathic Copyright Matix de l'invention du Seigneur Grillet, Hologur Paris, a calculating machine that would be more compact than Pascal's calculator and reversible for subtraction. The only two Grillet machines known have no carry mechanism, Displaying 3 lines of 9 independent dials, they also have 9 rotating Napier's rod for multiplication and division. Contrary to Grillet's claim, it was not a mechanical calculator after all. The 18th century. Overview. The 18th century saw the first mechanical calculator that could perform a multiplication automatically. Designed and built by Giovanni Pollini in 1709 and made of wood, it was the first successful calculating clock. For all the machines built in this century, division still required the operator to decide when to stop a repeated subtraction at each index, and therefore these machines were only providing a help in dividing, like an abacus. Both pinwheel calculators and Leibniz wheel calculators were built with a few unsuccessful attempts at their commercialization. Prototypes and limited runs. In 1709, the Italian Giovanni Pollini was the first to build a calculator that could multiply automatically. It used a pinwheel design, was the first operational calculating clock, and was made of wood. He destroyed it after hearing that Antonius Braun had received 10,000 guldens for dedicating a pinwheel machine of his own design to the Emperor Charles VI of Vienna. In 1725, the French Academy of Sciences certified a calculating machine derived from Pascal's calculator designed by La Copyright Pine, a French craftsman. The machine was a bridge in between Pascal's calculator and a calculating clock. The carry transmissions were performed simultaneously, like in a calculating clock, and therefore the machine must have jammed beyond a few simultaneous carry transmissions. In 1727, a German, Antonius Braun, presented the first fully functional 4-operations machine to Charles VI, Holy Roman Emperor, in Vienna. It was cylindrical in shape and was made of steel, silver and brass. It was finely decorated and looked like a Renaissance table clock. His dedication to the emperor engraved on the top of the machine also reads, "To make easy to ignorant people, addition, subtraction, multiplication and even division." In 1730, the French Academy of Sciences certified 3 machines designed by Hilaire de Bois de Sandeau. The first one used a single-tooth carry mechanism which, according to Bois de Sandeau, wouldn't work properly if a carry had to be moved more than 2 places. The 2 other machines used springs that were gradually armed until they released their energy when a carry had to be moved forward. It was similar to Pascal's calculator, but instead of using the energy of gravity, Bois de Sandeau used the energy stored into the springs. In 1770, Philipp Matthias Hahn, a German pastor, built 2 circular calculating machines based on Leibniz cylinders. J.C. Schuster, Hahn's brother-in-law, built a few machines of Hahn's design into the early 19th century. In 1775, Lord Stanhope of the United Kingdom designed a pinwheel machine. It was set in a rectangular box with a handle on the side. He also designed a machine using Leibniz wheels in 1777. In 1777, Stanhope produced the logic demonstrator, a machine designed to solve problems in formal logic. This device marked the beginning of a new approach to the solution of logical problems by mechanical methods. In 1784, Johann Helfrich Marr I Courteler built a machine very similar to Hahn's machine. The 19th century. Overview. The mechanical calculator industry started in 1851 when Thomas de Coma released his simplified arithmometer, which was the first machine that could be used daily in an office environment. For 40 years, the arithmometer was the only mechanical calculator available for sale and was sold all over the world. By then, in 1890, about 2,500 arithmometers had been sold, plus a few hundreds more from 2 licensed arithmometer clone makers. Felt and Tarrant, the only other competitor in true commercial production, had sold 100 comptometers in 3 years. The 19th century also saw the designs of Charles Babbage calculating machines, first with his difference engine, started in 1822, which was the first automatic calculator since it continuously used the results of the previous operation for the next one, and second with his analytical engine, which was the first programmable calculator, using Jacquard's cards to read program and data, that he started in 1834, and which gave the blueprint of the mainframe computers built in the middle of the 20th century. Desktop calculators produced. In 1851, Thomas de Coma simplified his arithmometer by removing the one-digit multiplier divider. This made it a simple adding machine, but thanks to its moving carriage used as an indexed accumulator, it still allowed for easy multiplication and division under operator control. The arithmometer was now adapted to the manufacturing capabilities of the time. Thomas could therefore manufacture consistently a sturdy and reliable machine. Manuals were printed and each machine was given a serial number. Its commercialization launched the mechanical calculator industry. Banks, insurance companies, government offices started to use the arithmometer in their day-to-day operations, slowly bringing mechanical desktop calculators into the office. In 1878, Burckhardt, of Germany, was the first to manufacture a clone of Thomas' arithmometer. Until then, Thomas de Coma had been the only manufacturer of desktop mechanical calculators in the world, and he had manufactured about 1,500 machines. Eventually 20 European companies will manufacture clones of Thomas' arithmometer until WWII. Dörfeld, in the U.S., patented the comptometer in 1886. It was the first successful key-driven adding and calculating machine. Key-driven refers to the fact that just pressing the keys causes the result to be calculated, no separate lever or crank has to be operated. Other machines are sometimes called key-set. In 1887, he joined with Robert Tarrant to form the Felt and Tarrant Manufacturing Company. The comptometer type calculator was the first machine to receive an all-electronic calculator engine in 1961. In 1890, WTO-DHNEA got the rights to manufacture his calculator back from Carl Paragraph Nixbger & C., which had held them since it was first patented in 1878, but had not really produced anything. ODHNEA used his St. Petersburg workshop to manufacture his calculator, and he built and sold 500 machines in 1890. This manufacturing operation shut down definitively in 1918 with 23,000 machines produced. The ODHNEA arithmometer was a redesigned version of the arithmometer of Thomas de Coma with a pinwheel engine, which made it cheaper to manufacture and gave it a smaller footprint while keeping the advantage of having the same user interface. In 1892, ODHNEA sold the Berlin branch of his factory, which he had opened a year earlier, to Grimm, Natalis & Company. They moved the factory to Braunschweig and sold their machines under the brand name of Brunsviga. This was the first of many companies which would sell and manufacture clones of ODHNEA's machine all over the world. Eventually millions were sold well into the 1970s. In 1892, William S. Burroughs began commercial manufacture of his printing adding calculator. Burroughs Corporation became one of the leading companies in the accounting machine and computer businesses. The Millionaire calculator was introduced in 1893. It allowed direct multiplication by any digit, one turn of the crank for each figure in the multiplier. It contained a mechanical product lookup table, providing units and tens digits by differing lengths of posts. 1. Another direct multiplier was part of the Moon-Hopkins billing machine. That company was acquired by Burroughs in the early 20th century. Automatic mechanical calculators equals. In 1822, Charles Babbage presented a small cogwheel assembly that demonstrated the operation of his difference engine, a mechanical calculator which would be capable of holding and manipulating 7 numbers of 31 decimal digits each. It was the first time that a calculating machine could work automatically using as input results from its previous operations. It was the first calculating machine to use a printer. The development of this machine, later called difference engine number 1, stopped around 1834. In 1847, Babbage began work on an improved difference engine design, his difference engine number 2. None of these designs were completely built by Babbage. In 1991, the London Science Museum followed Babbage's plans to build a working difference engine number 2 using the technology and materials available in the 19th century. In 1855, Per-Georg Skeets completed a working difference engine based on Babbage's design. The machine was the size of a piano, and was demonstrated at the Exposition in Iversell in Paris in 1855. It was used to create tables of logarithms. In 1875, Martin Wiberg redesigned the Babbage-Skeets difference engine and built a version that was the size of a sewing machine. Programmable mechanical calculators equals. In 1834, Babbage started to design his analytical engine, which will become the undisputed ancestor of the modern mainframe computer with two separate input streams for data and program, printers for outputting results, processing unit, memory and the first ever set of programming instructions. In the proposal that Howard Aiken gave IBM in 1937 while requesting funding for the Harvard Mark I, which became IBM's entry machine in the computer industry, we can read, "Few calculating machines have been designed strictly for application to scientific investigations, the notable exceptions being those of Charles Babbage and others who followed him." In 1812 Babbage conceived the idea of a calculating machine of a higher type than those previously constructed to be used for calculating and printing tables of mathematical functions. After abandoning the difference engine, Babbage devoted his energy to the design and construction of an analytical engine of far higher powers than the difference engine. In 1843, during the translation of a French article on the analytical engine, Ada Lovelace wrote, in one of the many notes she included, an algorithm to compute the Bernoulli numbers. This is considered the first computer program. From 1872 until 1910, Henry Babbage worked intermittently on creating the mill, the central processing unit of his father's machine. After a few setbacks, he gave in 1906 a successful demonstration of the mill which printed the first 44 multiples of pi with 29 places of figures. Cash registers equals. The cash register, invented by James Ritty in 1879, addressed the old problems of disorganization and dishonesty in business transactions. It was a pure adding machine coupled with a printer, a bell and a two-sided display that showed the paying party and the store owner, if he wanted to, the amount of money exchanged for the current transaction. The cash register was easy to use and, unlike genuine mechanical calculators, was needed and quickly adopted by a great number of businesses. 84 companies sold cash registers between 1888 and 1895, only 3 survived for any length of time. In 1890, 6 years after John Patterson started NCR Corporation, 20,000 machines had been sold by his company alone against a total of roughly 3,500 for all genuine calculators combined. By 1900, NCR had built 200,000 cash registers and there were more companies manufacturing them, compared to the Thomas Paine Arithmometer Company that had just sold around 3,300 and Burroughs had only sold 1,400 machines. Prototypes and limited runs equals. In 1820, Thomas de Coma patented the arithmometer. It was a true 4-operation machine with a 1-digit multiplier-divider. He spent the next 30 years and 300,000 francs developing his machine. This design was replaced in 1851 by the simplified arithmometer, which was only an adding machine. From 1840, Didier Rath patented and built a few calculating machines, one of which was a direct descendant of Pascal's calculator. In 1842, Timoleon Morel invented the arithmorel, based on the arithmometer, which could multiply two numbers by simply entering their values into the machine. In 1845, Azrael Abraham Starfel first exhibited a machine that was able to add, subtract, divide, multiply and obtain a square root. Around 1854, André Michel Goëri invented the ordonnanceur statistique, a cylindrical device designed to aid in summarizing the relations among data on moral variables. In 1872, Frank S. Baldwin in the U.S. invented a pinwheel calculator. In 1877 George B. Grant of Boston, Massachusetts, began producing the Grant mechanical calculating machine capable of addition, subtraction, multiplication and division. The machine measured 13 x 5 x 7 inches and contained 80 working pieces made of brass and tempered steel. It was first introduced to the public at the 1876 Centennial Exposition in Philadelphia. In 1883, Edmondson of the UK patented a circular step drum machine. 1900s to 1970s. Mechanical calculators reached their zenith. Two different classes of mechanisms had become established by this time, reciprocating and rotary. The former type of mechanism was operated typically by a limited travel hand crank. Some internal detailed operations took place on the pull, and others on the release part of a complete cycle. The illustrated 1914 machine is this type. The crank is vertical, on its right side. Later on, some of these mechanisms were operated by electric motors and reduction gearing that operated a crank and connecting rod to convert rotary motion to reciprocating. The latter, type, rotary, had at least one main shaft that made one, or more continuous revolution, one addition or subtraction per turn. Numerous designs, notably European calculators, had hand cranks, and locks to ensure that the cranks were returned to exact positions once a turn was complete. The first half of the 20th century saw the gradual development of the mechanical calculator mechanism. The Dalton adding listing machine introduced in 1902 was the first of its type to use only 10 keys, and became the first of many different models of 10-key add listers manufactured by many companies. In 1948 the miniature Curter calculator, which was held in one hand for operation, was introduced after being developed by Kurt Hestark in 1938. This was an extreme development of the stepped gear calculating mechanism. It subtracted by adding complements. Between the teeth for addition were teeth for subtraction. From the early 1900s through the 1960s, mechanical calculators dominated the desktop computing market. Major suppliers in the USA included Friden, Monroe, and SCM Marchant. These devices were motor-driven, and had movable carriages where results of calculations were displayed by dials. Nearly all keyboards were full. Each digit that could be entered had its own column of 9 keys, 1-9, plus a column clear key, permitting entry of several digits at once. One could call this parallel entry, by way of contrast with 10-key serial entry that was commonplace in mechanical adding machines, and is now universal in electronic calculators. Hills had a 10-key auxiliary keyboard for entering the multiplier when doing multiplication. Full keyboards generally had 10 columns, although some lower-cost machines had 8. Most machines made by the 3 companies mentioned did not print their results, although other companies, such as Olivetti, did make printing calculators. In these machines, addition and subtraction were performed in a single operation, as on a conventional adding machine, but multiplication and division were accomplished by repeated mechanical additions and subtractions. Friden made a calculator that also provided square roots, basically by doing division, but with added mechanism that automatically incremented the number in the keyboard in a systematic fashion. The last of the mechanical calculators were likely to have shortcut multiplication, and some 10-key, serial entry types had decimal point keys. However, decimal point keys required significant internal added complexity, and were offered only in the last designs to be made. Handheld mechanical calculators such as the 1948 Curter continued to be used until they were displaced by electronic calculators in the 1970s. Typical European 4-operation machines use the ODHNER mechanism, or variations of it. This kind of machine included the original ODHNER, Brunsviga and several following imitators, starting from Triumphator, Thales, Walther, Facet up to Toshiba. Although most of these were operated by hand cranks, there were motor-driven versions. Hammond calculators externally resembled pinwheel machines, but the setting lever positioned a cam that disengaged a drive pull when the dial had moved far enough. Although Dalton introduced in 1902 first 10-key printing adding machine, these features were not present in computing machines for many decades. Facet T was the first 10-key computing machine sold in large numbers. Olivetti Diver Summer 14 was the first computing machine with both printer and a 10-key keyboard. Full keyboard machines, including motor-driven ones, were also built until the 1960s. Among the major manufacturers were Mercedes Euclid, Archimedes, and MADAS in Europe. In the USA, Friden, Marchant, and Monroe were the principal makers of rotary calculators with carriages. Reciprocating calculators were made by Remington Rand and Burroughs, among others. All of these were key set. Felt and Tarrant made comptometers, as well as Victor, which were key-driven. The basic mechanism of the Friedan-Monroe, described above, was a modified Leibniz wheel. The Friedan had an elementary reversing drive between the body of the machine and the accumulator dials, so its main shaft always rotated in the same direction. The Swiss MADAS was similar. The Monroe, however, reversed direction of its main shaft to subtract. The earliest Marchants were pinwheel machines, but most of them were remarkably sophisticated rotary types. They ran at 1,300 addition cycles per minute if the plus bar is held down. Others were limited to 600 cycles per minute, because their accumulator dials started and stopped for every cycle. Marchant dials moved at a steady and proportional speed for continuing cycles. Most Marchants had a row of 9 keys on the extreme right, as shown in the photo of the figure-o-matic. These simply made the machine add for the number of cycles corresponding to the number on the key, and then shifted the carriage one place. Even 9 add cycles took only a short time. In a Marchant, near the beginning of a cycle, the accumulator dials moved downward into the dip, away from the openings in the cover. They engaged drive gears in the body of the machine, which rotated them at speeds proportional to the digit being fed to them, with added movement from carries created by dials to their right. At the completion of the cycle, the dials would be misaligned like the pointers in a traditional watt-hour meter. However, as they came up out of the dip, a constant lead disc cam realigned them by way of a spur gear differential. As well, carries for lower orders were added in by another, planetary differential. Accumulator. In any mechanical calculator, in effect, a gear, sector, or some similar device moves the accumulator by the number of gear teeth that corresponds to the digit being added or subtracted. A 3 teeth changes the position by a count of 3. The great majority of basic calculator mechanisms move the accumulator by starting, then moving at a constant speed, and stopping. In particular, stopping is critical, because to obtain fast operation, the accumulator needs to move quickly. Variants of Geneva drives typically block overshoot. However, 2 different basic mechanisms, the Mercedes-Euclid and the Marchant, move the dials at speeds corresponding to the digit being added or subtracted. A 1 moves the accumulator the slowest, and a 9 the fastest. In the Mercedes-Euclid, a long slotted lever, pivoted at one end, moves 9 racks endwise by distances proportional to the distance from the lever's pivot. Each rack has a drive pin that's moved by the slot. The rack for 1 is closest to the pivot, of course. For each keyboard digit, a sliding selector gear, much like that in the Leibniz wheel, engages the rack that corresponds to the digit entered. Of course, the accumulator changes either on the forward or reverse stroke, but not both. This mechanism is notably simple and relatively easy to manufacture. The Marchant, however, has, for every one of its 10 columns of keys, a 9-ratio pre-selector transmission with its output spur gear at the top of the machine's body. That gear engages the accumulator gearing. When one tries to work out the numbers of teeth in such a transmission, a straightforward approach leads one to consider a mechanism like that in mechanical gasoline pump registers, used to indicate the total price. However, this mechanism is seriously bulky, and utterly impractical for a calculator. 90-tooth gears are likely to be found in the gas pump. Practical gears in the computing parts of a calculator cannot have 90 teeth. They would be either too big, or too delicate. Given that 9 ratios per column implies significant complexity, a Marchant contains a few hundred individual gears in all, many in its accumulator. Basically, the accumulator dial has to rotate 36 degrees for a 1, and 324 degrees for a 9, not allowing for incoming carries. At some point in the gearing, one tooth needs to pass for a 1, and 9 teeth for a 9. There's no way to develop the needed movement from a drive shaft that rotates 1 revolution per cycle with few gears having practical numbers of teeth. The Marchant, therefore, has 3 drive shafts to feed the little transmissions. For one cycle, they rotate 1/2, 1/4, and 1/12 of a revolution. 2. The 1/2 turn shaft carries gears with 12, 14, 16, and 18 teeth, corresponding to digits 6, 7, 8, and 9. The 1/4 turn shaft carries gears with 12, 16, and 20 teeth, for 3, 4, and 5. Digits 1 and 2 are handled by 12 and 24 tooth gears on the 1/12th revolution shaft. Practical design places the 12th rev shaft more distant, so the 1/4 turn shaft carries freely rotating 24 and 12 tooth idler gears. For subtraction, the drive shaft's reverse direction. In the early part of the cycle, one of 5 pendants moves off-center to engage the appropriate drive gear for the selected digit. If possible, see John Wolfe's website, 3, for a superb collection of photos with some accompanying explanations. He has similar sets of photos for several other notable calculators. Some machines had as many as 20 columns in their full keyboards. The monster in this field was the duodecillion made by Burroughs for exhibit purposes. For sterling currency, a pound-d, there were variations of the basic mechanisms, in particular with different numbers of gear teeth and accumulator dial positions. To accommodate shillings and pence, extra columns were added for the tens digit, s, 10 and 20 for shillings, and 10 for pence. Of course, these functioned as radix 20 and radix 12 mechanisms. A variant of the marchant, called the binary octal marchant, was a radix 8 machine. It was sold to check very early vacuum tube binary computers for accuracy. As well, there was a twin marchant, comprising 2 pin-heel marchants with a common drive crank and reversing gearbox. 4. The article at the link describes them and shows a twin Brunsviga. Twin machines were relatively rare, and apparently were used for surveying calculations. At least one triple machine was made. It's likely that a given accumulator could be engaged with either half of the twin. The facet calculator, and one similar to it, are basically pin-heel machines, but the array of pin-heels moves sidewise, instead of the carriage. The pin-heels are binary. Digits 1 through 4 cause the corresponding number of sliding pins to extend from the surface. Digits 5 through 9 also extend a 5-tooth sector as well as the same pins for 6 through 9. The keys operate cams that operate a swinging lever to first unlock the pin positioning cam that's part of the pin-heel mechanism. Further movement of the lever rotates the pin positioning cam to extend the necessary number of pins. 5. Stylus-operated adders with circular slots for the stylus, and side-by-side wheels, as made by Sterling Plastics, had an ingenious anti-overshoot mechanism to ensure accurate carries. The end of an era. Mechanical calculators continued to be sold, though in rapidly decreasing numbers, into the early 1970s, with many of the manufacturers closing down or being taken over. Comptometer-type calculators were often retained for much longer to be used for adding and listing duties, especially in accounting, since a trained and skilled operator could enter all the digits of a number in one movement of the hands on a comptometer quicker than was possible serially with a 10-key electronic calculator. In fact, it was quicker to enter larger digits in 2 strokes using only the lower numbered keys. For instance, a 9 would be entered as 4 followed by 5. Some key-driven calculators had keys for every column, but only 1 through 5. They were correspondingly compact. The spread of the computer rather than the simple electronic calculator put an end to the comptometer. Also, by the end of the 1970s, the slide rule had become obsolete. See also, abacus, adding machine, calculator, history of computing hardware, mechanical computer, tabulating machine, George Brown. References. Sources: De la machine à calculer de Pascal à l'ordinateur. Paris, France, Musa Copyright National des Techniques, CNAM. 1990. ISBN 2-908207-07-9. Trojman, G. Netasov, A. Computing in Russia. Germany, G.W. Viereg. ISBN 3-528-05757-2. Felt, Dori Mechanical Arithmetic, or the History of the Counting Machine. Chicago, Washington Institute. Marguin, Jean. Histoire des instruments et machines à calcul, trois siècles de ma copyright conique pensanti 1642–1942. Herman. ISBN 978-2-7056-6166-3. Morlevat, Guy. Les machines arithmétiques copyright de Blaise Pascal. Clermont-Ferrand, Lafrena sections d'édition d'imprimerie. Tatin, Rena copyright. Histoire du calcul. KSG. Na degree 198. Presses universitaires de France. Turk, J.A.V. Origin of Modern Calculating Machines. The Western Society of Engineers. Reprinted by Arno Press, 1972 ISBN 0-405-04730-4. Ginsberg, Jacuthiel. Scripta Mathematica. Kessinger Publishing, LLC. ISBN 978-0-7661-3835-3. Martin, Ernst. The Charles Babbage Institute, ed. The Calculating Machines Translation from Die Maschinen. Cambridge, Massachusetts, The MIT Press. Cohen, I. Bernard. Howard Aiken, Portrait of a Computer Pioneer. Cambridge, Massachusetts, The MIT Press. ISBN 9780262-531795. Smith, David Eugene. A Source Book in Mathematics. New York and London, McGraw-Hill Book Company, Incorporated. Moseley, Maboth. Irascible Genius, Charles Babbage Inventor. London, Hutchinson and Company, Limited. Bowden, B.V. Faster Than Thought. New York, Toronto, London, Pittman Publishing Corporation. Williams, Michael. A History of Computing Technology. Los Alamitos, California, IEEE Computer Society. ISBN 0-8186-7739-2. Randall, Brian. The Origins of Digital Computers, Selected Papers. Springer Verlag. ISBN 3-540-06169-X. IBM. A Calculator Chronicle, 300 Years of Counting and Reckoning Tools. New York. Collier, Bruce. The Little Engine That Could Have, The Calculating Machines of Charles Babbage. Garland Publishing Incorporated. ISBN 0-8240-0043-9. Essinger, James. Jacquard's Web. Oxford University Press. ISBN 0-19-280577-0. Hook, Diana H. Norman, Jeremy M. Origins of Cyberspace. Novato, California, HistoRifeScience.com. ISBN 0-930405-85-4. Professor S. Chapman. Blaise Pascal Tercentenary of the Calculating Machine. Nature 150, 508 to 509 doi, 10.1038/150508 AO. Usage de la machine. Courrier du Centre International Blaise Pascal, 4 €25. 1986. External links.